The pressure gradient force pushes air from high pressure toward low pressure. So, if that were the only important force, we would expect the wind to accelerate directly toward lower pressure. But when we look at the free atmosphere, something surprising happens. The wind often blows almost parallel to the pressure or on upper air maps or geopotential-height contours rather than directly across them. So here is our question. Why doesn't the wind simply follow the pressure gradient force? What turns the air? To answer that, we are going to follow a single air parcel and begin with one of important physics law or Newton's law. The air parcel accelerates only if the forces do not balance. The important forces are pressure gradient force, Coriolis force, friction, and gravity. Pressure gradient force pushes air from high pressure toward low pressure. Coriolis is not a real push in an inertial frame. It appears because we observe the motion from the rotating Earth. For example, in the northern hemisphere, if an air parcel is moving from south to north, it deflected to its right as shown in this figure. Friction is crucial, close to the ground, but much weaker aloft. Gravity matters primarily in the vertical and is nearly balanced by the vertical pressure gradient force through hydrostatic balance. Here, we are going to set up the next simplification. In the free atmosphere, we can often keep only pressure gradient force and Coriolis force in horizontal balance. Near the Earth's surface, the wind does not usually follow isobars perfectly. It crosses them at an angle toward lower pressure. The reason is friction. Friction slows the wind. And because the Coriolis force depends on wind speed, Coriolis becomes weaker. The pressure gradient force is therefore not completely balanced, leaving a component of motion toward low pressure. Now, imagine moving upward away from the surface. We are not going to top of atmosphere. We are simply leaving the frictional boundary layer and entering the free atmosphere. Surface friction rapidly becomes much less important. For large, slowly evolving weather systems, the horizontal acceleration can also be relatively small compared with the two dominant forces. Then something remarkable happens. That's called geostrophic balance. Imagine a warm atmospheric column in the south and a colder column further north. Before discussing geostrophic wind, we first need to decide how we are looking at the atmosphere. We will begin with a constant height surface, and later in the second part video, we will switch to the constant pressure surfaces that meteorologists normally use for upper air maps. On the constant height surface as shown here, atmospheric pressure can vary from one location to another, and we represent these horizontal pressure differences using isobars as shown here. Because warm air expands, warm southern atmospheric column is thicker than the cold northern column. If surface pressure are initially similar, then at sufficiently high altitude the pressure tends to be higher over warm southern column and lower over the colder northern column. So we have a horizontal pressure gradient from south toward north, and the pressure gradient force points toward the north. Now comes the interesting question. If the pressure gradient force is pointing northward, why doesn't the air simply continue accelerating toward the north? The answer comes from Earth rotation and Coriolis force. This figure on the left is the standard geostrophic story. At first, a parcel feels a pressure gradient force from high pressure to low pressure, as you see in this figure, and there is no Coriolis force because particle is not moving. As soon as it starts moving, the Coriolis force appears at the right angles to its motion in the northern hemisphere. At each point, we see that Coriolis force is increasing and deflecting wind towards its right. The wind keeps turning until Coriolis force points opposite the pressure gradient force. At that moment, there is no horizontal acceleration across isobars, which is really important, and the wind flows parallel to the isobars. In short, if low pressure is north and high pressure is south, the wind direction that balances the northward pressure gradient force is eastward. To summarize, at high altitude, more precisely in the free atmosphere, the wind does not blow directly from high to low pressure. Instead, because the Coriolis force nearly balances the pressure gradient force, the wind flows approximately parallel to the pressure or geopotential-height contours. So the low and high are not detached. They remain dynamically connected through the pressure field. Where the contours are closely spaced, the pressure gradient is stronger, and therefore the geostrophic wind is stronger. Where the contours are widely spaced, the pressure gradient is weaker and the corresponding geostrophic wind is weaker. But this idealized balance has an important consequence. Because there is little or no cross-contour motion, horizontal convergence and divergence become very weak. Air tends to circulate around the low and high rather than moving strongly across the contours. In other words, the inward cross-contour motion that we might expect toward a low and the outward cross-contour motion from a high are strongly suppressed in the ideal geostrophic picture. The pressure systems are still connected, but the direct redistribution of air masses through convergence and divergence becomes very limited. This tells something important. A perfectly geostrophic atmospheric cannot by itself explain how real high and low pressure systems intensify, weakens, or produce substantial vertical motion. For that, we need small departures from geostrophic balance, which is called the ageostrophic flow. The geostrophic wind explains the main direction of the wind, but real weather comes from the small departure from the geostrophic balance. This ageostrophic part allows air to cross contours near the surface. Of course, friction causes convergence into lows and divergence from highs. Aloft, ageostrophic divergence and convergence help lows deepens or weakens. Therefore, a purely geostrophic atmosphere is useful but not fully realistic. In the next part, I will explain and derive formulation related to the geostrophic wind.